I'll give just a quick intro for Justin here. So thanks for coming all the way from out east here. Justin Shultz, he got his bachelor's in energy engineering from Penn State, along with minors in environmental engineering and energy business and finance, which sounds fun. He went on to get his PhD from the Center for Architecture Science and Ecology at the Rensselaer Polytechnic Institute in New York. His PhD, we were talking about it a little bit earlier, included modeling strategies for dynamic building envelopes for future energy technologies. So has a lot of background in various modeling tools. He's currently a building performance analyst at EYP, working within the HighPerformance design group, and guides architects and engineers through an integrated design process, which we at the Integrated Design Lab love to hear people using that. And Justin uses quantified metrics from his modeling and climate analysis to provide performance-based recommendations to those teams. So look forward to hearing about methods and some case studies. And thanks for joining us today, Justin.
Thanks, Damon. So I'll be presenting today on modeling tools to inform early design. A little bit about myself. As Damon already introduced myself, I'm from EYP Architecture and Engineering. We're an integrated architectural and engineering firm. I'm part of the High Performance Design Group, which really works as an integrated member of any design group to really quantify any decision being made by the architects or engineers on energy metrics or occupancy comfort metrics. My title is a Building Performance Analyst. Damon already went through kind of my background, but what really motivated me was during my senior year as an energy engineer at Penn State, I discovered how big of a consumer buildings are within our energy sector. And that coupled with a senior research project in building energy modeling really sent me on a trajectory of understanding what these tools can do and how we can use them to assess our building and really design more energy efficient buildings in the long run. Where I then ended up at EYP working with architects and engineers who are retrofitting and designing new buildings to design more energy efficient buildings and better buildings for occupants. So amongst the group, I'm really a tools expert. Sorry, we got this wiggly problem going on with the connection. It's not going away this time. There we go. So I'm a bit of a tools expert. I use a wide range of building energy modeling tools ranging from IES, OpenStudio, Energy Plus, a few building CAD tools like Revit, Autodesk, or Autodesk Suite, Rhino, and some parametric tools including Dynamo and Grasshopper, as well as a tool called System Advisory Model, which is really tool for assessing renewable energy technology, which I'll show a few examples of those, as well as several scripting languages, which are all kind of necessary throughout the process. So what is high performance design? High performance design is a holistic design approach which minimizes resources, improves the environment inside and outside, operates efficiently with flexibility to adapt, and creates rich productive environments. However, this ends up making this kind of triangle of balances between resources, occupants, and improved environment. But there's a new wing of this that's kind of becoming much more relevant, which is resiliency. As we move forward, we got to think about the impacts of climate change and the impacts that our energy infrastructure has on our buildings and our occupants as a whole, and whether or not we can use more sustainable or better performing buildings to deliver a more resilient building that doesn't rely so much on the grid or uses less energy and then doesn't have a negative impact on surrounding grid structures. So what we explore is a wide range of design options or design potential. So a lot of it is building geometry exploration. We help the architects either typically on new construction say, what is the most optimal form, or can you design your building form differently that is more efficient for the given climate, particularly south and west facades? Do you want to have a big west and east exposure that would get a lot of solar heat gain in the morning and afternoon. That can be beneficial for some buildings, but it might be negatively impactful for other buildings. Shading feasibility, passive design strategies like the Passive House Institute of the US, they have these standards for very airtight, highly insulated buildings. You may have seen the Icebox challenge floating around on the internet recently, where they're putting these ice boxes in the middle of a city. They have a code building, which is just a box with ice inside of it, and then a passive house building where it's highly energy efficient, or highly insulated, we should say. And the difference between the amount of ice in there after a week is phenomenal. And you can see that the passive house has significantly more ice inside, which really kind of shows a stabilization of temperature inside, where if it were a building, you'd have occupants. So we look at these kind of considerations and we balance them out with local codes and also energy and cost, because at the end of the day, if the client isn't interested in the cost of the project, we need to rationalize it for them. So what this really comes down to is the simple model, which is better for people, better for the environment. It's really simple, but that is the sweet spot we try and find. And somewhere maybe in the third dimension here is the cost that we're balancing, because a lot of these different strategies come with an added cost. So at EYP, we've been ranked the top 3 in the nation for sustainability for the last 5 years. For the last 3 of those, we've been ranked number 1. So what we do is kind of a 3-phase approach. We look at the research. When we first get dropped into a project, we really research the climate as well as client goals and opportunities. We brainstorm strategies, what makes sense for this project based upon the local climate, based upon the appetite of the client themselves, and what could be the low-hanging fruit, and what might we be able to convince them of on a longer-term strategy, or where can we even make a building that has these features to plug into in the future. And then we evaluate with analysis. We start doing energy modeling, daylighting simulation, and energy generation simulations to really inform the design with hard numbers, things that people can really wrap their heads around instead of just kind of arbitrarily suggesting them. So to go into a little more detail, we from the get-go, stage 1, we start gathering data. What is the climate telling us that could be beneficial for this project? Is orientation a factor? Is winter-to-wall ratio relevant? Is solar heat gain something we need to address? For example, a lot of Chinese projects, solar heat gain isn't a driving factor because a lot of overcast climates in Lake Guangzhou, for example. So we need to actually look at things that are more insulating, where the outside temperature and moisture is a real problem. As well as the owner program requirements and other requirements such as state code, or some campus buildings have their own executive orders that we have to follow. And we use that to evaluate opportunities with regards to passive schemes, building orientation, and solar radiation or rain. These climate analyses can be done in kind of a number of stages, but really early on we start assessing quantities for outside dry bulb temperature, universal thermal climate index, or UTCI, which is a factor of how comfortable is someone based upon wind, solar, and clothing index at that time of the year. Solar radiation and a lot of different factors, which I'll show more specifically on given projects later. The second stage is brainstorming, as I mentioned, where we're optimizing building for site with site improvements as well as indoor environment, and focusing on the people, what would be best for the occupants in the space. Are they residents, or are they workers that are coming to the space temporarily? What is really the schedule that drives these buildings? So here we start identifying strategies with regards to what mechanical systems start making sense, what satisfy peak load. If we start looking at a system like ice storage, or you're recharging it at night, if you have a building that has a near 24-hour operation, ice storage is not a feasible strategy for you. But if you have a building that completely empties out during the evening, you can start utilizing off-peak HVAC system strategies. You also want to think about thermal comfort, daylight harvesting, view to the outdoors, and solar glare. So these are all brainstorming ideas that we think of and strategies that we come about. But until we start evaluating them, we don't really suggest them to the client, because unless we can back up our claims with some kind of quantitative metric, then it's harder to sell it to a client or a building occupant. So these evaluations come in the form of massing studies, daylighting analysis, energy modeling, computational fluid dynamics on occasion, where we start looking at natural ventilation, moisture control, and water balance calculations. So next I'll show you, and there's actually quite a lot of examples, how we start utilizing several different tools that we've used in-house and tools that are available on the market to really deliver on a project. So some examples of how HPD or high performance design can help. So we have a project example here from Eastern Virginia Medical School. We first started with a climate analysis before we even really understood where this building was going or what kind of strategies that they were going to employ. We wanted to understand what were the factors that really would drive the energy consumption in the building. Is this a hot climate? What's the solar radiation resource like? Luckily in Virginia, we have a pretty moderate climate. It can get quite hot, but it can get cool as well. So we looked at kind of what timeframes might be feasible for things like natural ventilation or using solar radiation to our advantage. But we don't want to work in a vacuum of just historic weather data. We also want to look at future weather data. We started looking at weather data that is coming from predictive models for 2035, 2065, and 2090. These dates are kind of arbitrary, but you want to really consider the buildings with regards to floodplains. Are rising sea levels going to have a negative impact on our current buildings? Do we need to lift it an extra foot? That's something that you can do at the very beginning of a project that is not going to have that big of a factor. But if you waited until they broke ground, it's too late. But we start looking at, in addition to future weather data, we want to understand what's the loads on our building. Is this a predominantly cooling or heating driven building? Most of the time we have heating driven buildings, but we also have a cheap source of heating available to us. But is there ways in which we can offload this heating and instead use it positively? Our buildings are also predominantly internally driven by heat. So might we be able to utilize some of that internal heat gain when we're considering the heating degree days and instead downsize mechanical equipment based upon the loads of the actual building itself and the occupants? So things like psychrometric charts are commonly employed just to help us assess what percentage of the year are we really in an acceptable comfort where we can use free cooling. That's not always an available option for us, but we use tools like Ladybug to help us assess a lot of these climatic factors, including wind direction, but not only wind direction, but overlaying this, and it's pretty hard to see here, additional information with regards to the local drop temperature. At which points are we actually seeing the temperature of the climate? So at certain times of the year, we're getting wind predominantly from a particular direction, but is that wind cold? Is it hot? Is it going to negatively impact our building? Do we need additional air tightness to keep out certain timeframes? So as we look at the heating condition, so from about 7 a.m. to 10 p.m. most of the time in a day where the building's really kicking up back into full operation, we see that the temperature is actually quite warm throughout a large portion of our year. The length of the bar is predominantly based upon frequency as well as the temperature. And we can use these factors to help us assess things like natural ventilation. We did, however, only figure out that natural ventilation, due to the moisture content, was only feasible about 10% of the year in this project. But that was something where, does it make sense to use operable windows for our building? In a medical center, it didn't really make sense, but there was a lot of advantages to exploring this and setting up this method for other projects as well. So next, on the same project, now that we start looking at the massing, we want to study things like solar radiation. Solar radiation in of itself can be informational, that's not the right word, informational. But anyway, the point is solar radiation on a building alone is not a good metric for your assessment of the building. we see that a large amount of solar radiation based upon the red color here is actually reaching or impacting the south and eastern facades of this building. Notice the north orientation on the top right, and a lot less on the northwest and northeast. However, if we think about the times of the year in which the solar radiation is actually received on the building envelope, if we think about the fact that during the winter, the solar angles are much lower, so we're getting a lot more solar radiation on our east and south facades, predominantly in this orientation. We actually see that this solar radiation is beneficial to our building because the outside air temperature is colder than our design condition or our set point temperature. So that solar heat gain is passively heating up our building during the winter when we actually do want that morning sun impacting our building and heating it up. However, you'll see that on the northwest and south northeast, it's not receiving the solar radiation at all. So throughout the winter, it's actually losing a lot of heat, which means we want to reduce the amount of window to wall ratio on those orientations because we would lose more heat than we would gain due to passive solar heating on those orientations. So this is just a very quick study we can do on a massing to help the designer assess where to focus their window to wall ratio, where to focus their views, and where it might negatively impact the building if they move. So additionally, we want to study daylighting. There's a big consideration of how much of our floor plate is actually receiving daylighting even before we start putting in enclosures, occupancy rooms, and assessing these quantities. However, it's also important to understand the annual solar exposure, or ASE, which is a metric of overexposure of daylight, which can be a factor of solar heat gain, or it can be a factor of glare. So it kind of determines the probability. So in this climate, we determined that 99.9% of the space has a annual solar exposure greater than 250 hours, which makes it not eligible for the LEED credit. However, in future designs of this project, they actually started integrating more overhangs to help take out that solar heat gain during the summertime when it is most intense. So additionally to this project, we wanted to study things like renewable energy generation. What is the potential for this project to integrate things like photovoltaic panels? So we assessed the actual feasible area for solar panels. We could have put it in the northern section of this, but because of the angle of the sun, it doesn't make sense. We'd actually be out of operation for a significant number of hours of the year. So we focused the solar panels in the feasible regions of the building and assessed that it would be able to generate about 225,000 kilowatt hours per year, which we then compared against a baseline energy code. So if we took the building and just followed ASHRAE 90.1 for the local climate, which was 5, we basically set up our baseline. We then applied a number of energy efficiency measures with regards to higher performing windows, insulation, mechanical systems to reduce the heating and cooling loads, and then could further employ the solar panels to bring down that energy and really give them an annual amount of energy savings that range from 18.5 all the way down to 16.5 beyond our proposed design. So another 16.5 from solar panels. So another project this one was a very early design stage daylighting analysis, where they were really curious about this light well space that they were designing right here. The building itself had this basically interior space which they wanted to design to have daylight throughout the year, but it was unsure if a fully exposed glass roof would overexpose that space. Would there be so much daylight that it would either be hot or too bright? People wouldn't want to sit there and occupy the space, making it an active space for students and faculty to meet or collaborate? Or do we need a clear story where we're blocking out some more of that solar radiation, but then not allowing as much daylighting? So a very simple daylighting analysis set up in Ladybug and Honeybee was established here, where we could just basically create this enclosure space, the building that we were designing, and assess how much solar radiation or daylight, sorry, is being received at the floor here. And you can see between the left being this really glass exposure in this clear story on the right, that the clear story actually blocks out so much solar radiation or daylight that it would really create a much more dim and dark space than we'd want for this kind of outside like feel. So beyond that, we started doing some renderings to kind of help us feel what this space would be like. This one being done in Enscape, which is a plugin for Revit, really quick to turn around a rendering for within your Revit environment. You set up a view, and you're able to quickly look through that view to your space and the materiality and daylight appropriate for that. We also did an additional study where another tool which we're utilizing more and more called Lighting Analysis for Revit is a plugin for the Revit environment which allows you to do the daylighting studies directly within the same environment that the architects are designing their buildings, which makes the information exchange that much faster for them, allowing them to do some of the analysis themselves, or as I'll show you later, update the building based upon what we can see from this, while an analysis previously would have taken considerably longer because you have to take the information out and you have to set up in radiance and do all these other additional steps. So we had a few professional renderings done that kind of helped us elaborate what this space would look like. But when we actually went there and took photographs itself, we've realized that the space itself is a lot more diffuse and uniform than we originally expected. The daylight quality is quite neutral. It's not this bright condition we see here at the bottom where occupants sitting in at those couches there might be kind of squinting as they're looking at their neighbor next to them who's sitting in the sun, but instead a much more uniform space where they're able to work on their textbooks and laptops without too much glare on their computers or discomfort or solar heat gain. So another daylighting study that we did, as well as a PV study for federal building modernization projects. I would say about half of our projects are also retrofits and updates to existing buildings. We do a lot of work, I should have mentioned earlier, in the education institution sector, campus buildings, as well as federal buildings. This one I can't name, but you can generalize, as well as National Park Service and several projects along those lines. So in this, we were setting up another light well, really simple analysis that we wanted to study here. We were taking this space kind of just south of those windows that you can see in the basement level and elevating the ground up to create this outside pavilion that the occupants of the building could go and have their lunch outside while being protected by the building's kind of shape. But we were worried, does elevating this pavilion mean that the people sitting in the basement have less daylight proportional to where they were before? So we did a quick study using Rhino, Grasshopper, and Diva. Diva is another daylighting tool. It uses the Radiance engine, but it's just really quick to send mass and geometry right into the model, set up a grid to study. We realized between the without the light well and with the light well that there was very minimal changes to the actual quality in those spaces. The floor plate that we studied was probably much larger than we needed, because the occupants' offices are really just this perimeter space on the bottom section of that space. We realized that the light well does not negatively impact the daylight quality in those spaces. So we then scaled up to a much larger study. We had an entire building floor plate. The existing condition, being the one on the left here, had a lot of opaque enclosures. They really loved their office spaces, the ability to close their office and have a private space. However, we wanted to try and convey to them that those kinds of solid enclosures are, one, not great for collaboration or density of your workers, as well as daylighting quality, because it blocks much of the daylight that would otherwise penetrate deeper into the space, which this building, and how long ago it was built, was really meant to utilize much of the daylight available, but yet they've since enclosed many of those spaces off. Said, all right, what if you start using things like glass partitions, ones where you have a closed office, but instead you have a glassy wall that may have some kind of milk glass or the Frity glass that has, actually we can see it right here where it has the opaque characteristics, but yet still allows light to transfer through. And we could show them that the daylight actually penetrated much deeper into the floor plate than you would have otherwise seen with their enclosure, allowing them to reach a much larger percentage of their building area. We then also looked at a few other options where maybe we enclose certain sections of the building, only moving down to 50% enclosure space and 25% enclosure space, focusing maybe specifically on the wings. And this really was used to meet with the client. A lot of this information has brought them back to the clients to really try and help drive decisions. A lot of our interior designers are really interested in driving the client to a more open floor plate design, one where you could have desks instead of individual offices. And this was used to meet with the client to convince them to move to a less enclosed space. So we did another photovoltaic feasibility study for this one. This one we took a section of the southern roof area and determined the amount of basically available system area. We discounted that by I believe it was 25%. For loss of space, you really can't put PV panels from edge to edge. And we used a tool called System Advisory Model, or SAM. It's a tool developed and provided by the National Renewable Energy Lab, or NREL, right there in Golden, Colorado. And it's a tool that really builds on top of the PV Watt, if people are familiar with PV Watt, but really gives you much greater control of how your system is actually being designed. And it allows you to select the individual modules, your tilt, your how you're stringing them up in series or parallel, and really you have total control. You don't need to have control every single parameter, but it does give you a lot better control over things like payback. So we could take from the National Renewable Energy Lab, they quantified the actual cost of PV panels per watt or kilowatt in this circumstance. You get a lot of diminishing cost over a much larger system, but you can quantify what's the cost of your the actual panels, what's the cost of the labor, what's the cost of the inverters, as well as other systems that all combine to make the technology itself. All of this cost information was put directly into SAM, allowing us to get the most up-to-date based upon the 2017 report that they had released, and give the most up-to-date quantification of the actual cost of PV panels. A lot of people say, oh, but PV panels are so expensive. And you're saying, no, they've actually come down in cost a lot in the last few years. Well, how much? So we're able to then bring this information directly into SAM and quantify the actual cost of the different arrays that we were reviewing, and then couple that with the utility rate information based upon peak loads and just general electricity consumption. We could then quantify the monthly PV energy generation, and then also the cost payback of the tax flow or the cash flow, which is how much are you putting in to purchase the system based upon the cost information I explained. And this was done as a really quick study. Took maybe a couple hours just to set up, because the system advisory model, this tool really makes it easy to, you step through it. You say, all right, which module am I choosing? How big is the system? What's the cost information? What's the utility information? And each of those allowed us to then put in the information and provide an actual payback of 11.5 years. This is without any subsidies, and it was for this given project. The client was originally considering no PV panels. They said, no way, the cost payback is so high, it's not worth it. Well, as a federal building, they're in these buildings for years and years and years. So now they're actually considering, maybe we should put PV panels, which this was a pretty quick study. We turned around early design before really meeting with an electrical engineer or any of these factors that may, or a third-party consultant to quantify this and convince the client that it might be feasible to really look at these factors. So I want to show you some of the tools now that I've been using more directly with the architecture teams at an early design phase, before maybe even the geometry is set up, or as the geometry is being generated, providing them energy information right there, very iteratively, very quickly. So this is a new dormitory project for Hood College. We used what's called Insight 360. It's an Autodesk tool. There's a plugin for Revit if you're interested in trying it out yourself. You basically take the geometry that's being generated within Revit, and you can immediately send it out to their clouds. It runs about 300 parametric simulations, which I'll actually show you a little demo and gives you weighted averages of what's the impact of different design decisions on your energy consumption. That these factors include building orientation, lighting, wall construction, infiltration, glass, and even HVAC systems. So this project was a pretty conventional dormitory following the kind of architectural design they already had on campus. And we were able to set up a really quick energy model right within Insight 360 and send it out to the cloud. So this this environment gives kind of these let me just show the demo. So the demo is actually, it's a lot more exciting when you see it in person. So this is the project itself. We were able to take the geometry that was set up in Revit and directly send it out here to the cloud, where it runs a whole series of iterative studies. It gives you a benchmark. So if we set up a scenario where we have this baseline, let me use the updated baseline. So if we use this baseline scenario, which I set up to follow an ASHRAE 90.1 baseline definition, and give me a second. Yeah. Oh, good point. Good point. Thank you. I forgot to bring it over. There we go. Much better. Okay. So the interface itself is a web-based interface. This gives you a lot of interactive control over how you operate with the building itself. You can set up different scenarios with regards to your building geometry. We're looking at several different phasing options, phasing 1, 5-story option, 4-story options, and we're able to then compare what is the energy use intensity or the dollars per square foot, so it quantifies the electrical and thermal or natural gas consumption of the different building geometries, and then quantifies how much that costs. And you can compare them on an apples-to-apples basis by setting up scenarios. So if I take this baseline scenario and update this simulation, you can see that they compare the several different options on a apples-to-apples basis, allowing you to compare different massing options. You can actually get a lot more controlled once this updates with regards. So you can compare it. It shows, based upon it being quite a large number of simulations that it runs, it has a range of available options to you. We at the time didn't know the window-to-wall ratio, so we left it open to a wider range of window-to-wall ratios that could be an option. So it gives you not only just one value, which is the solid line here, which is the mean, but also a max and min, or a distribution of potential energy consumption, because it runs something like 300 simulations. So if I go into a single option here, we actually have a lot of control over how we study and what information can be given to the design team. So so we have our geometry set up. You can explore it here. It's a very simplified version of what you saw before. I've done some more detailed ones, but this one's a good example. And you can actually compare things like building orientation. And you'll see that for this project, building orientation had a minimal impact on the design. So it's actually the slope of the points here, as well as the markers at the top, dictate really what level of impact this has on your energy consumption. So each of these might be pretty small, but let's say we look at the west facade. Well, right now we're looking at basically a double pane window. If you guys watch this slope, which goes from about maybe 5.8 down to 3.9, and we say, let's go to a triple pane window, which is the last option here, and you can see it's the best performing one by reducing our energy use intensity, or energy consumption per square foot of the building, by a 3.79 kBTUs from our baseline. Then you can actually see that the slope, or the relative impact of the window-to-wall ratio, decreases. So now that we're using triple pane windows, high performing windows, the impact of the window-to-wall ratio becomes less. Now, I'm going to show you this as an example. It's obviously not feasible for building code, but if we went to single pane, you could see that this is a much larger impact, that your window-to-wall ratio has a much larger impact on your design. This allows us to then sit with architects and really show them what is the weight of their decisions, where we update a parameter and all the other parameters across the whole simulation update. So if we were to change all of these and basically set up maybe a 30% window-to-wall ratio, and we went down to the mechanical systems here, you would see that the mechanical system has a much larger impact now on energy because the total energy of our building may be more or less depending upon the heating or cooling loads. This can also look at occupancy schedules, several daylighting controls, plug loads. Lighting efficiency is one of my favorites because there's the code requirements, and then there's LED lighting, which is becoming very common now, and you can really push into much lower efficiencies. So this is kind of how we operate it with it when we're sitting with the architects and engineers as a part of the design. But it's also relevant to understand how we're presenting this work to the client, because we're using this information at the interview stage, at the point at which we're sitting with the client for the first time and showing, hey, this is what we can do for you guys, and we want to win this project for you. So this information has been pointed at a few times, particularly in Hood College. Basically the board said one of the key decisions they had in choosing EYP for the project was that we were already thinking about energy. At the interview, we were already integrating energy and the way in which we can use energy to save them money in their operational energy costs, or annual operational energy costs, at the interview, at the very, very beginning. No one else that presented had any kind of any quantification like that. So having this information very, very early on is very powerful and helping us inform and make decisions. So as I mentioned, we set up these baseline scenarios. That's really just, I set these up manually based upon ASHRAE codes local to the climate. And we start understanding what's the relative weight, as I mentioned, of these different design decisions. For example, LED lighting has a very big impact on lighting, particularly for this building, which is a fairly large 4-story dormitory. And we could quantify that based upon the utility rates of the client themselves, how much they'll save every year by switching over to LED lights. That can then be used against things like the cost of switching from LED lights from incandescents, and we can use this to do simple paybacks as well, even at the interview or very early in the project. We can also use it for improved envelope insulation and airtightness, where we move from codes into higher performing envelopes and more airtight buildings, and use it to quantify energy savings from improved building envelopes, which is actually, I found out recently from cost estimators that the whole industry is moving towards much more insulating envelopes. So the cost of going towards higher R values is actually not very expensive. As well as HVAC systems. The HVAC system modeling in this is a bit, I would say it's pretty rough. They're not really modeling every HVAC configuration. They're using much more simplified COP values for their energy efficiency values and such. So they're not doing a thorough energy analysis with regards to the HVAC system, but this platform does allow you to take the models that you're generating in Insight 360 and export them to things like DOE2 or Energy Plus, and pick up those models and start manipulating them yourself if you have more thorough things to study. And we could quantify things like HVAC systems. So this allows us to then really quantify as a combined aspect. Individually, each of those numbers are great, but what is it when you combine all of them? You're going to LED lights, that reduces your heat gain in the space. That means that your heating load's going to then increase. So there's a lot of factors that need to be balanced out, and when considering them all, you can quantify and create a scenario like I did here, where I created a scenario with all of the factors combined to assess the impact it had on energy. And we could see that this bar now substantially decreases. It went from 90 something, I think it was before. And you can actually see that as you step through these scenarios, each of these bars in the middle here is your model history. So as you're making changes, you can track the history or impact you have on the model, as well as the range in which of options. It's really doing an averaging of your conditions, and it gives you kind of how much variability you have. So we could use this to then quantify things like different scenarios and compare them on what impact it has on energy, so kBTUs per square foot, or energy use intensity, or we can look at this in terms of US dollars per square foot per year of operational energy costs. And we can compare the operational energy costs of different options and use that to quantify our operational energy savings for the client. So this was also applied on another project. This one was even more aggressive in terms of how we utilize this Insight 360. They have an existing building, so this is actually a retrofit project instead of a new construction. We took an existing building situation, calculated the energy use intensity as well as the operational energy. This one, the operational energy is probably not great to focus on because we didn't have great utility rates for the client, which is a campus building, so they have reduced utility rates. But we could use this to then quantify how far from an existing, so if we retrofit their building to code, and then also they were curious, what if we went all the way to the passive house standard? What if we increased our insulation and air tightness? What impact would that have on our building energy consumption? We were able to study that before the interview for this project. So very similarly to what we did last time with an even larger building where there's 2 towers, they're actually taking the towers and joining them together in the middle. So it's quite a large amount of building area and quite a large retrofit project. We can assess things like the LED lightings as it is described, code-based envelopes following ASHRAE 91 for the climate zone, and quantify the new energy use intensity following code compliant and impacting it with the new, integrating it with a new design from the architects themselves, where they're basically coupling the 2 buildings with this space in the middle and producing more dormitories and really iterate through each of their options and apply different standards to their project. And then moving a step further into the Passive House Institute US measures, which incorporate higher improved envelope insulation and air tightness, an additional 23,000 in savings. This is on top of the code standard, as well as they basically mandate triple pane windows. So another 62,000 from that as well for this climate. So with that, actually that was not on top of the baseline. It was on top of the existing. So combined 73,000 savings, and then we could compare these for the client against their existing and code compliance and show them, what's the value of going all the way to passive house standard, or maybe stopping at the code compliance, or maybe somewhere in between. And we want to work with them, and we tell them right at the interview, we'd love to work with them to figure out what they find is the most cost effective for their project, and also quantify that on energy use consumption and energy savings. So lastly, I want to show you some of the energy modeling tools that we're using. And particularly at an early design stage, typically energy modeling is saved for much later when you really have the building geometry defined, where you have the building already set by the architects, maybe program set, and at that point you might not have as much control over the building as you would have otherwise wished you did as a designer of the energy consumption for the project. So we're starting using much more shoebox models or even prototype building energy analysis. So if you're familiar with CBEC's Commercial Building Energy Consumption Survey, they did a huge study of an average office building, an average school. They surveyed, I think, 140,000 buildings and quantified what is the average energy consumption for each of these different building types in different climates, in different hot climates or temperate climates, and they from that also produced what is the average building geometry for those types of buildings. So for this project, we were looking at a school, so we could actually from this menu here select a prototype building that matched our school. So that we have a primary school and secondary school. So instead of just doing a shoebox model, which is typically just a single room where you're testing things out, we're actually scaling up our prototype shoebox models to the size of the building. So we took the secondary school option and we actually modified it a little bit to set up the actual area requirements of our project. Before the architects have nailed down their design, their program, their building massing, any of those options, we're able to sit down with this and say, all right, well, what if we're looking at different mechanical systems or occupancy sensors or insulation characteristics. So we're able to use these prototype buildings without a lot of details needed from the other models. So This allows us to then set up mechanical systems for this project. We were really curious if an air-cooled chiller or a water-cooled chiller made the most sense. We had some limitations on the project that the water-cooled chiller was, which may not fit into the building, unfortunately. So we started saying, all right, what negative impact will we have if we went to the air-cooled chiller? We know water-cooleds are more efficient. Can we, make it up in other ways? So we studied, we basically set up a mechanical system from a template. They have, a lot of these tools now have templates built into them. You can just say select ASHRAE System 5 or System 7, which is an air-cooled, or it's a VAV with reheat, or a water-cooled chiller. And you start changing these parameters very early on. So just using the massing I described here, with the relative areas that we would expect on our actual building project, we could assess things, we can assess on energy consumption, on energy use, and energy costs. And these reports then output right into a report that can be sent to reviewing agencies like LEED. So instead of having to take up their spreadsheet and put in all the information again, so you already have all the information in your building energy model, then you have to reproduce it all into the spreadsheet for LEED. You can actually output these reports directly for LEED, and you just upload the report, reducing the amount of transfer. So this project's going for the integrated design credit. So we needed to show, even at the 35% submission, that we're already looking at energy modeling options, which in this case was this prototype shoebox model. We're able to pick this up very quickly, utilize it on the project, and turn around for LEED, and as well as informing the mechanical designers on the project what system made the most sense. So this same project then also started looking at daylighting analysis. We wanted to understand, as it's a classroom building, we should be able to optimize most of the occupied space towards the perimeter of the building, as well as faculty offices. So we were able to do another lighting analysis for Revit. This was done very early on, and we could assess what amount of daylighting are we receiving. So things like this gymnasium at the north part of the image here, we actually designed clear story spaces to understand, is this gymnasium receiving enough daylight over the course of the year? And we actually realized that we could. And this information was then sent back to the architects and say, actually, the windows in the faculty offices, they're not really working out. This in the top right, the ARC building, is actually a black box theater, so we don't want daylight there, so that doesn't negatively impact us. But the faculty offices on the east and north segments here are actually not receiving enough daylight, and we would want to optimize those windows better. And maybe regions like in this ARC, which personally I'm very concerned about because I worry it's going to get too much daylight, I could show them in quantified metrics that it does in fact receive too much daylight. So we actually only get 27% of the building area meets the SDA, or spatial daylight autonomy. So how much daylight is it receiving throughout the year? And less than 10% area above the annual solar exposure, which I explained prior. But what's nice is it shows a breakdown. It says, all right, well, actually, we're receiving enough daylight for 69% of our building, but 42% of our building is also receiving an overexposure of daylight. So if you subtract those two, you get the remaining 27%. So I can point directly to these areas and say, hey, this comes out, I don't know if you're familiar with Revit, this actually comes out as a schedule as well. You can show it directly to the architect and point to the spaces that are a problem. And you can show them these are the spaces that are receiving too much light, and work with them to design either smaller windows or overhangs, or what other scenarios would make the most sense to then bring the annual solar exposure down for the given project. So that was a lot of information, a lot of projects very quickly. Any questions regarding the tools we use or the method we use, or something I didn't show you that you're curious about, feel free to ask away.
One question.
Mm-hmm.
I love that you're modeling for resiliency and climate change, and it looks like you're looking at various IPCC scenarios in that. Is there a scenario that you use as a default when you're, the most informative?
Yeah.
As far as that goes?
I think we tend to use, I guess 2050 is probably our low-hanging fruit. That's where we start with. Depending upon whether or not the client is very concerned about it. For example, we have some OBO projects that we work on. We really start looking much further out, where they're really considering these factors. So 2050 tends to be our starting place, and then we might step from there.
Yeah. And then a second question real quick. Do you, I assume you must create weather files based on that data.
Mm-hmm.
I can do that using media norm software, but do you have a tool that you use for that?
So we tend to buy them. There's a lot of assumptions that go into how they're made. You know, part of my PhD, I looked into it a little bit. And you know, there's the high, low, and medium kind of scenarios that you can set up. We tend to just buy a scenario because, you know, we don't want to go too deep into there and then find out we made the wrong assumption. So I think you can buy them for like $75 each. So it's not too bad. Yeah.
Awesome. Thank you.
Yep.
I have a question about that first medical school one you showed had kind of an idiosyncratic design or very specific design,
Mm-hmm.
and all of your analysis looked like you were starting with that. So on that one, did you come in kind of later than you would have preferred?
Great question. So the site was very restrictive. They wanted to basically put it on this corner of an intersection and really just fit it into the last square foot of their campus. So the actual design was kind of set by the site boundaries. Yeah, a lot of times we're brought in too late, and what we're doing is with these tools that are becoming easier and easier to use, we're showing, hey, we can be there right at the beginning. We can help you from the get-go. So yes, part of that design was already set. It happened to work out in that project that the design was well optimized for solar heat gain, for example, in that scenario where we got a lot in the south and southeast. But there are a number of projects where we're brought in too late, and we say, hey, can you change this? And they say, no, it's already set, and that's the unfortunate truth. There's at the end of the day, there's only so much that our team of specialists, which are 2 to 3 people on average, can do across a firm of about 500 people. So we try our best to turn around a lot, but we're definitely looking to scale up the teams to help with that bandwidth.
And in an office like yours, when a new project comes in, are you assigned right from the start to?
Yes, that's becoming much more commonplace for us that that we have skills that are being evaluated and appreciated. Previously, a lot of our methods were too slow. We'd say, hey, they come in for an interview and say, hey, is this design doing better in energy? And it'd take us, a few weeks or months to really set up the energy model to a place where we're comfortable. And now there's tools like cloud-based tools with Insight 360 and some of the prototype buildings that we can use very early on. So the fact that we're turning around these results and clients are actually really, really receptive to the information means that we're getting picked up much more frequently, yes.
You mentioned at the top that you got some scripting experience,
Mm-hmm.
you said in Python. Do you find yourself using that much in the early stage modeling, or do you find that the packaged tools are adequate for the early stage modeling, and you save that more for writing a custom OpenStudio measure or something like that later on?
Great question. So it tends to be that the scripting is definitely more helpful later on. It tends to be that we don't have the time to really create our own scripts. Some of these competitions we hear about maybe a week before we actually have to give the interview, or 2 weeks. And that might not be enough time to really set up a script and troubleshoot and make sure it's working the way we need it to. So we tend to use the tools that are available. However, we're definitely interested in exploring more scripting methods. We're starting to look into, Dynamo, for example, is a great example of that's built on Python. And so we're able to start setting up custom scripts in Dynamo that are automatically making changes to the Revit model, which maybe the architect put too many details in the model that we need for our energy model. So we actually need to automatically turn off certain elements throughout the building. So we're creating scripts that do that, translate it really quick, and makes it so that I don't need to pick up every project and turn off all these elements and hide certain things and send it out for the analysis, but it does it all for us automatically. So there's definitely tools that we're making ease of use, but it tends to be tools that make, or scripts, sorry, that make the tools easier to use that we're already using. So, but a lot of the work is end up doing scripting where we're automating tasks too. We just don't have a lot of automated tasks right now. Yep.
I'm curious about that NREL, that free program that they have you had any success with real projects on how close the estimates they spit out are? Or?
Great question. We have taken the so where we tend to notice the comparison is with regards to the cost estimator. So we'll estimate a particular cost based upon the NREL report, and then we'll get a local cost estimator to confirm our cost estimates based upon what they're seeing on projects locally. So are the local installers charging more or less than the national average? And we hear feedback there, and it tends to be a little more. I think because the market's so competitive right now that a lot of people are installing a lot of solar panels that there's you know, some people that are having trouble, you know, keeping up with the demand. But it's also doesn't account for things like a city. So this project was in Washington, D.C., for example, and the cost of installing solar panels in Washington, D.C. obviously comes with an added cost of the traffic and siting and getting a crane to get them up there, or you know, whatever method you decide to get them up there. So there was some added cost for local considerations that tended to change. In terms of energy production, it's pretty spot on. I mean, over the course of a year, our energy, the calculations, there's a lot of studies that have looked at, you know, what is our weather files showing versus what is our actual local solar radiation availability, and they're actually quite close over the course of a year if you average them out. So the actual generation potential is quite good, and the system advisory model is very powerful because it takes into account of degradation over time. You know, the inverters and the panels becoming less efficient, needing to replace the inverters every 10 years or, you know, a certain life cycle. So it actually takes into those account those considerations when doing the cost assessment. So it's pretty accurate at the end of the day.
Online questions. One is how does the tool Climate Consultant compare to the tools that you showed to analyze weather, wind, etc.?
So I did show one Climate Consultant slide. It tends to be that throughout the industry, we're using Climate Consultant a lot less. For those that are not familiar with Climate Consultant, it's a tool that takes weather information and outputs a series of climate weather graphics, such as the one I showed previously. And it, you know, it can do a lot for you automatically. If you're unfamiliar with the climate information, it can provide a lot of really good information quickly. But once you understand what this information is relevant for, you actually want to start manipulating the data a lot more. For example, with those wind roses that we were showing, we can actually overlay not only the wind direction, but also temperature with it. And it doesn't allow you to do those custom features. So we need to start kind of hacking our way into information that's relevant for a project. So we end up using Ladybug and Grasshopper, which is Ladybug and Honeybee, which is a Grasshopper plugin, which allows us to do kind of scripting. It's node-based scripting where you drop in a node and there's script behind it and you connect them and inputs and outputs, and it's kind of like it's a graphical scripting interface, if you're familiar with those. So sometimes we make custom components if needed, but we end up needing to do a lot more manipulation of the data ourselves, and it ends up being that the graphics that come out of Climate Consultant are becoming kind of stale, unfortunately. I'm being totally honest here. I hope the person who didn't ask is a developer of Climate Consultant, but we're just finding them that the client isn't really picking up the information quickly and understanding what it means. So we have to take the information and kind of put it into a graphical interface for us, or graphical notation the client understands. Because if we're just showing like this slide earlier, which is just a whole bunch of weather information, and we just show that the client has no idea what any of this means. So we need to translate the information for them, and that often comes in the form of taking the climate information and creating our own graphics. So we end up doing a lot more without climate consultant these days.
Okay, great. And then another question from Jason Glazer. Have you been using the new ASHRAE standard 209 at all?
We have. So that's where some of the shoebox modeling at the very end came about. We use 209. They have shoebox modeling requirements. So basically, they tell you at each phase of a project, you should be doing this analysis or this. Don't go this far yet. Stop here. There should be enough information for you. And part of that was the prototype modeling that we did because LEED is following a lot of that same trajectory. So their integrated design credit accounts for many of those factors of what kind of modeling is being done at each stage. So they're working very well in parallel, which from my understanding as my boss, Teresa Rainey, as actually part of the team has 189 and worked closely with 209. Has said that LEED and 209 have been working very closely together to understand, what needs to be done at each stage and what is actually relevant for a project.
Cool. All right. Well, it's 1 o'clock, so we can let you stop. But thank you very much for your time.
Yeah. If anyone has any further questions, feel free to email me, connect with me on LinkedIn or Twitter, or discuss with me after this.
And then for those that are here, there are a couple prizes. Your odds are probably pretty good of winning today, I'm just going to say. And our next in-person BSAG is going to be combined with the ASHRAE group. It'll be December 12th. And we'll have Drew Crawley, who is kind of one of the original developers of Energy Plus. And he'll be talking either kind of what goes into energy modeling or how to integrate simulation with BIM tools. So that keep December 12th on your calendar. Let me grab the things. And then you've also got evaluation forms if you wouldn't mind filling them out. And then we'll have